These are the notes for AP Calculus on the topic of factoring, simplifying, and solving equations and inequalities using factoring. So let's start with a little review of factoring. Instructions here say to factor completely. So remember, the first thing when you're factoring that you always should look for is what's called a greatest common factor, or we often use the acronym GCF for short. And that's what all the terms, some factor all the terms have in common that we can factor out. So on this first polynomial, there's two terms. You can tell how many terms are separate depending on how many plus or minus signs separate them. So in this case, the 81x is the first term, and x to the fifth is the second term. And you look for what those two terms have in common. You can see the only thing they have in common is x, and factor it out to the lowest exponent, which is just 1. And once you do that, you put an open parentheses, and then put down what's left of each term. In other words, if you were to distribute this x back, what would this have to be to give you back what you had originally? So we factored out the x, we're still left with 81. Let's see, x times 81 would give you 81x, minus x times what would give you x to the fifth. Well, we factored out 1x, so there's x to the fourth left. So in this case, x is our GCF. Now, once you've taken that out, sometimes there might be factoring you can use beyond that. In this case, there is, because you can see we've got two terms, and this fits the form of difference of perfect squares. If you can figure out what square gives you each of those, then you can factor it further. In this case, 9 squared is 81, and x squared squared is x to the fourth. So, difference of perfect squares, factors like this. Since 9 was first, be 9 minus x squared is one of the factors, and then 9 plus x squared is the other factor. You can see why this would work, because 9 times 9 would give you 81. And then you'd have on the out, 9 times x squared would be positive 9x squared, 9 times negative x squared would be negative 9x squared, and those are going to cancel. And then you would have negative x squared times positive x squared would give you negative x to the fourth. And then don't forget to bring down the GCF of x. And then you want to look and see if either one of these can factor further. Well, you'll notice that 9 minus x squared is another difference of perfect squares. You figure out what square gives you each of those. Let's see, what square gives you 9? That's 3. And what square gives you x squared? That's x. So in a similar fashion, since the 3 is first, I would factor into 3 minus x and 3 plus x. Well, what about a sum of perfect squares? Now, the difference means it's a minus, those can factor. If you have a sum of perfect squares, like 9 plus x squared, that does not factor any further. So that one, we'll just leave. That's 9 plus x squared. And then don't forget, we'll also bring down our GCF originally of x. So now this is completely factored. There's no more factoring we can do at this point. And if you were to multiply those all back together, combine like terms, you would get back 81x minus x to the fifth. Okay. So the factors are all the things that multiply to give you the original polynomial. All right, let's take a look at another one. This one starts out, the first example started out as a binomial. It had two terms. Notice this one, 3x to the fourth minus 5x to the third minus 12x squared. This is what's called a trinomial. We've got three terms. So again, let's look for the GCF first before we do anything else. So look at the coefficients, 3, 5, and 12. Well, other than 1, there's nothing we can factor out there, but we've got variables x to the fourth, x to the third, and x squared. And just like we did over here, we can factor out the GCF of x. In this case, the lowest exponent is 2. On the first example, the lowest exponent was 1. So we can factor out x squared. Let's see what that leaves us with. So then we're left with 3 is still there, and then x squared times x squared would give you x to the fourth, minus 5 is still there. There's 1x left, because x times x squared would give you x cubed, minus just the 12, because we factored out the x squared. So now we've got the GCF of x squared factor out. Now we've got a trinomial left. Let's see if this factors any further or not. So to see if it does, when you have a trinomial, you multiply the first term, coefficient of the first term times the coefficient of the last term. In this case, 3 times negative 12 gives you negative 36, and we want to find factors of negative 36 whose sum is the coefficient of the middle term, negative 5. Let's see if anything works or not. In this case, you can see 9 times negative 4 would give, negative 9 times positive 4 would give you a negative 36, and their sum, negative 9 and positive 4, would give you negative 5. So negative 9 and positive 4 would work. So then what you do is you leave the 3x squared alone, and you use these two numbers we figured out, negative 9 and 4, to split up the middle term. So instead of negative 5x, we'll split that up as negative 9x and positive 4x. That's really, if you combine those, it's the same as negative 5x, right? And then you leave the minus 12 alone. Now we've got 4 terms, and when we have 4 terms, now we can try to use group factoring on this. So split in half after the second term, and then just take out the GCF of each of the binomials here. So the first 2 terms, the GCF is 3x. And when we take that out, we're left with x minus 3. And the second 2 terms, the GCF is a positive 4. And we're left with x minus 3. And now, we look at the whole thing and look and see, if you think of this as like the first term, those are multiplied together, plus this is like the second term. And now we take out the GCF of those, which, if you do this correctly, should be the terms in parentheses. You can see they both have an x minus 3. So you factor out the x minus 3 as a GCF out of both of them. And then what we have left, well, what's left of the first term is just the 3x, plus what's left of the second term is just 4. And finally, don't forget our GCF we took out in the very beginning was x squared. And now look and see if either of those factor further, and they do not. So that is our completely factored form. All right, now let's take a look at simplifying rational expressions using factoring. So let's start with this one. It just happens to be t instead of x. Really, you could use any variable. T and x are the most common variables we use in calculus. So you look at the numerator first, 15 minus 3t. Again, always look for a GCF first. Let's see, the GCF here would be 3. And then what's left of the 15 would be 5, minus what's left of the 3t would just be t. So that's how we can factor the numerator. And then on the denominator, let's see, t squared minus 25, that fits the difference of perfect squares. Factoring. So you figure out what squared gives you t squared. Well, that's just t. What squared gives you 25 is 5. So that's a factor into t minus 5 and t plus 5. Then we want to see if anything reduces here. So is there anything, it's the same on the numerator and denominator, because anything divided by itself is just 1 and it can be reduced. So the question is, well, we've got 5 minus t and t minus 5. Are those the same or not? Easy way to tell when you're not sure about something like that, algebraically, is to just put in concrete numbers. So if we had, instead of t, we had, let's say, 2. 5 minus 2 versus 2 minus 5. Are those the same or not? Well, 5 minus 2 is 3. 2 minus 5 is negative 3. So you can say they're not the same. They're actually the opposite. So the way to get them to be the same so we can actually reduce it is to actually factor a negative 1 out of one of them. Doesn't matter which one. So let's say we factor it out of the numerator. If we factor a negative 1 out of the 5 minus t, that'll make that a negative 3. And look at what that does. If you factor out a negative 1, I'm going to switch the order here, because now that negative is gone from the t, so that'll actually be a positive t. And if you factor a negative 1 out of the 5, that changes the sign to be a negative 5. You can see if you multiply it out, you get the same thing you did here. You get negative 3t, which is what we have here. And negative 3 times negative 5 would be a positive 15. So it's the same expression, just in a different form. And that's useful because now when we have on the denominator t minus 5 and t plus 5, then you can see we've got t minus 5 divided by t minus 5. Any expression divided by itself And one that's not 0 is 1. So those are reduced out, those just equal 1, and so all that's left in our simplified form would be negative 3 over, and I'm going to drop the parentheses on the t plus 5 because there's no longer anything to multiply by. If you left the parentheses, that would be fine as well. All right, let's take a look at the denominator now. So let's try to use factoring here. Right now you can look at the numerator and say, okay, well here's the first term, and then plus, here's the second term. The question is, if we look for a GCF there, is there any GCF? Well, this has x, this has 4, that's the one. This has 4 minus 3x, this has x squared plus 1, so there is no GCF in that case. So what can we do to simplify? Well, if there's no GCF, like there was on the second example here, then actually it's helpful, it might be helpful to distribute it out, to actually multiply it out first before we try to factor. So x times 4 is 4x. And then distribute the x times negative 3x, negative 3x squared. Then if we distribute out the positive 4 times x squared, you get 4x squared. And positive 4 times 1 is positive 4. Let's do that first. And the denominator is a lot easier. We can start by factoring out the GCF, which you can see is just x. On those two, that binomial, and they have in common. Then you take out the x, you're left with x squared minus 4. So now, let's simplify the numerator here. So let's combine our like terms. So if you have 4x squared minus 3x squared, that's just x squared. And we got plus 4x, and then plus 4. The denominator, you can see you can factor that a little further. X squared minus 4, again, that's a difference in perfect squares. What squared gives you each of those? Well, what squared gives you x squared would be x, what squared gives you 4 would be 2. So that would factor in x minus 2 and x plus 2. And then don't forget the GCF of x out in front. Now that we've combined our like terms on the numerator, let's see if that factors. It's a trinomial again, like the example up here. But this time the coefficient on parentheses was just 1, so that's a little easier. 1 times 4, so you find factors of 4. Whose sum is 4. Total work there would be 2 and 2. So that would factor into. This time you don't have to split up the middle term like we did here. We could, but when it has a coefficient of 1, it's a little easier to use a shortcut and just jump right to the factored form. It would just be x plus 2 and x plus 2. You could split up the middle term like we did here and use group factoring. You'd get the same answer. This is just a little bit more efficient. And then in the denominator, we've got x minus 2, and x plus 2. So now you can, they're both completely factored on the numerator and denominator. You can look for anything that reduces. You can see x plus 2 divided by x plus 2, that's just 1, so those reduce out. And that's it. So our final answer here we have x plus 2, there's nothing left to multiply by. You can drop the parentheses over x times x minus 2. And if you want to distribute out the denominator, you can, x on the denominator, but you don't have to. Okay, now let's take a look at using factoring to solve equations first of all. And then we'll look at using factoring to solve inequalities. So to solve this equation, first thing to remember, factoring is only useful when you're trying to solve an equation if one side of the equation or some, as we'll see, inequality equals 0. We'll see 0 has some special properties. If one side is not equal to 0, factoring is really not helpful at all in solving equations or inequalities. So for instance, if we just tried to factor the 6x squared minus 11x and took out an x, you'd be left with 6x minus 11. It's not helpful because it's equal to -4, and there's an infinite number of different things that multiply to be -4. However, if we get it equal to 0 first, by adding the 4, then we'll have 6x squared minus 11x plus 4 equals 0. So now we've got the right side equal to 0 here. And again, we've got a trinomial. So we can see 6 times 4 for factors of 24. You want the sum to be the coefficient of no term, and it's getting -11. So let's see if anything would work there. Well, let's see, -8 and -3 would work there. So this one we can't use the shortcut because it's got a 6 as a coefficient of the leading term, unlike the last problem had a 1 there. So you just leave the first term alone again. And again, what we do is we use the -8 and -3 to split up the middle term. So instead of -11x, that's the same as -8x and -3x. And it doesn't really matter what order you put those in. Your steps will look a little different if you put the -3 first and the -8 second, but your final answer will still end up being the same. Now you got 4 terms, so now you can split it in half and factor out the GCF of each binomial. So the GCF of the first 2 terms, you can see, would be 2x. And that will leave us with 3x minus 4. Now here, whenever the second term, second pair of binomials I should say, has a leading coefficient that's negative, you always have to factor out the negative in order to get to match up. So in this case, there's nothing you can factor out as GCF except for the -1 in this case. So you factor out a -1, and that changes the sign of the first term to be a positive 3x, and the positive 4 changes it to be a -1. And again, you can see, think of this as the first term here, and this is the second term. You can see what they have in common, taken out of GCF, is the 3x minus 4. So you can pull that out as a GCF, 3x minus 4. And then what's left is we've got 2x left in the first term, once we factor out the 3x minus 4, minus 1 in the second term. Now it's completely factored and it's equal to 0, so here's where having it equal to 0 is so important. When a number of factors multiply to be 0, okay, there's something we know for certain. The only way you can multiply things and get 0 is if one of the things you're multiplying is 0, right? So, but we don't know necessarily which one, so it could be either one. So either this 3x minus 4 has to equal 0, that's one possibility, or the 2x minus 1 has to equal 0. And then you just solve each one of these. You add the 4 over on both sides, you get 3x equals 4. Divide by 3 gives you x equals 4/3. And on this one, you would just add the 1 to both sides. They give you 2x equals 1. Divide by 2, so x would equal 1/2. So those would be your 2 solutions. And when there's more than one solution, oftentimes you'll see the answer written like this. X equals, you use the little braces, or sometimes I call it the squiggly bracket. So, and then usually they're written from lowest to highest. So 1/2 is smaller, and then 4/3, and then a closed brace. All right, let's take a look at one more. It look a little more complicated than you're used to seeing, but it's really not as hard as you might think. Oftentimes students will see this and they'll try to multiply this all out, which you could try doing, and you might be able to get a factor that way and solve, but it's generally going to be a lot more difficult than it needs to be. So, kind of like we did right here at this step, think of, since these are multiplied together, there's our plus sign, think of this as like your first term, plus these are multiplied together here, so this is like your second term. Now remember, the first thing you always look for in factoring is a GCF. Notice this one's already equal to 0, so unlike the last problem, we can start by factoring right away since one side is already 0. So let's find our GCF by looking for what do these have in common. Well, you can see they both have 2x minus 1, This one is squared, this one is cubed. Remember, just like in the other variables that are in both, for all the terms, you factor out to the lowest exponent. So in this case, 2 is the lowest exponent, so we can factor out 2x minus 1 squared. That's part of our GCF. Is there anything else they have in common? Well, yes, this has x plus 3 squared, and this has x plus 3. Again, the lowest exponent here is 1, though. So you just factor out x plus 3 out of both terms. So that's our GCF. Then after you take out the GCF, you put an open parentheses and put down what's left of each term. So let's see what's left of the first term. Well, we took out a 2x minus 1 squared, so that's completely gone. We factored out one of the x plus 3's, but it was squared, so there's still one of them left over. So we still have an x plus 3 left over. And then don't forget this plus sign is still there, so plus. On the second term, we took out the x plus 3, so that's completely gone. But we factored out 2x minus 1 squared, and here it was cubed, so you still have one of those 2x minus 1's left. Okay. So we took out the GCF of 2x minus 1 squared, x plus 3, and this is what was left. So now, we've almost got it in completely factored form. You can see these two as their GCF, those are already completely factored. And then all we have to do is combine our like terms over here. So we've got 2x plus x is 3x, and 3 minus 1 is 2. And now see if any of those factor further, and none of them do. So now once it's completely factored, again, the only way this can equal 0, and this, once it's in factored form, is if one of these equals 0. Notice the squared here really doesn't affect our solutions for when it equals 0, because if 0 is squared, it's still going to be 0. So really just going to be any exponent. Now when it will affect it is if inequality, we'll see on the next example problems, but for the equations equal to 0, one of these has to be 0. So either the 2x minus 1 has to equal 0, so that's squared, that would still be 0, equal 0. Or the x plus 3 has to equal 0, or the 3x plus 2 has to equal 0. That's the only way these factors can multiply to be 0, so if one of them is 0. So let's solve each of these separately. So here you would add the 1 to both sides, you get 2x equals 1, divide by 2, gives you x equals 1/2. On this one you'd subtract the 3 from both sides, give you x equals negative 3. This one you would first subtract the 2 from both sides, would give you 3x equals negative 2, and then divide by 3 on both sides, would give you x equals negative 2/3. So this time we have 3 solutions. So again, usually the way it's written is x equals, use the braces, open braces. And typically they're written from lowest to highest, so our lowest answer would be negative 3, then negative 2/3, then 1/2. Okay, now let's move on to solving inequalities using factoring. And a lot of the steps look similar to equations, but there are some key differences that are very important, distinctions between inequalities and equations you want to make sure you understand. Okay. So first, what is an inequality? Well, an inequality is when it's not just equal to, it's either greater than or less than or equal to, or greater than or equal to. So you can see this one is greater than or equal to, this one is less than. All right, and we want to be comfortable using 2 different types of notation. So we're going to write our answers on these problems in 2 different ways. One using inequality notation. Sorry about that. And the other one using interval notation. So let's start with this one. It starts off similarly in that you need one side of the inequality to be 0, just like the equation. So here we're going to subtract 2 first of all. Well, it's not equal to, it's greater than or equal to 0. After we subtract 2 from both sides, and then you want to factor it. So we want factors of negative 2, we want the sum to be 1. So that would be 2 and negative 1. Multiply the negative 2 out to be 1. But this time we can use a shortcut because it just has a 1 out in front. So this would factor into x plus 2 and x minus 1. So it's saying this is greater than or equal to 0. So far, you notice the steps are just like equations. Here's where it's going to get a little bit different though. Okay? Let me show you the most common mistake I see students make. So this next thing, don't write it down. I just want you to see the logically why this doesn't make sense, this common mistake. Okay? So what I see commonly is students will try to approach this the same way as an equation, and they'll say, okay, well, we split it up in an equation when it was equal to 0, so why can't we just split it up on the same way in the inequality? Say x plus 2 is greater than 0, or x minus 1 is greater than or equal to 0. Okay, now these are multiplied together, right? So let's see why this doesn't make sense logically. Well, this is saying, if you solve these, that both of these have to be positive numbers. Well, that would work, right? A positive times a positive would give you something greater than 0. However, is that the only way we can get a positive number? No. You could also have a negative times a negative would also give you a positive. So saying that both of these have to be greater than 0 is false. They don't have to be. They could both be less than 0, but now it's don't, right? So we don't solve it this way at all, in a sense. Okay, what we do is first figure out where it's equal to 0. So you solve it like you would an equation here, and that you put equal to. Because that would give us some of the solutions, right? Where it equals 0 says greater than or equal to 0. Let's first figure out what makes it equal to 0. And you can see when you solve each of these, this one gives you x equals negative 2. Add the 1, this one gives you x equals 1. So those are the places where it equals 0. And then what you do next is you actually draw yourself a number line. And we're going to use a number line quite a bit for a variety of different things as a tool to analyze what's happening. So on this number line, the only key numbers we need to put down are the ones we got here, negative 2 and 1. Let's put them in order. And what we know, well, what is going to put down what we know about these? Okay? We know that both of these make, because if this is 0, one of them 0, the whole thing when you multiply together is going to be 0. So that both of these, if you put these in for x, make it exactly equal to 0. That's inequality. But what we want to know is where is it greater than 0 as well as equal to 0. So these are two of our solutions, but they're not necessarily the only ones. So then what we can do next is pick a number in each of these intervals on the number line and test it into our inequality. The factored form is the easiest place to test as opposed to the original one. And all we're concerned with is whether it's positive or negative. Yeah. So let's say we test negative 3. Negative 3 is less than negative 2, right? So in this factored form, we don't need to know the exact value. If you plugged in here, you could do that too. That would still work, it would just take longer. We just need to know if it's positive or negative. So negative 3 plus 2 is negative, right? Negative 3 minus 1 is also negative. A negative times a negative is positive. So we know not just negative 3, but anything over here, because these are the only two places that are 0, would have to be positive. Negative times negative. Now let's test something between negative 2 and 1. Well, probably the easiest thing to test there is 0. 0 is between negative 2 and 1. If we test 0, 0 plus 2 is positive. 0 minus 1 is negative. A positive times a negative is negative. So not only 0, but everything between negative 2 and 1 would be negative. Finally, let's test something greater than 1 over here on the number line. So let's say we test 2. If you test 2, 2 plus 2 is positive. 2 minus 1 is positive. A positive times a positive is positive. So now, let's see if we can write our answer in the two different ways. We're looking for where this is greater than or equal to 0. In other words, where it's positive or 0. So you can see our solutions are where it's positive and 0 and not where it's negative. If the sign was flipped the other way, if it was less than or equal to 0, then our solution would be where it's 0 or negative in between. So let's write an inequality notation first. So let's look at this interval here. We can say x is, because that's a variable, less than or equal to negative 2. It's really, if we were to graph this on the number line, our solution here, this is a where it's equal to 0 as a solution, as well as everything over here that makes it positive. So really writing that down, that interval down. And same thing here, 1 is a solution because it says or equal to 0, or everything to greater than 1 this way is also a solution. So we can say x is less than or equal to -2, or, that's one possibility, x is greater than or equal to 1. So that's one way we're going to write our solution down. That's inequality notation. Let's also write it down in interval notation. In interval notation, you go from left to right, starting with the lowest and going to the highest. In this case, this goes forever to the left. That takes you to negative infinity. And on negative infinity, you never use a bracket in interval notation. You always use a parenthesis. So for negative infinity, that's where it starts, the interval, comma, and it stops at -2. And -2 is included because of the equal to, so we use a bracket there. And then the other interval we have, we can put a little union because we're joining all these intervals together here. That's the symbol for union. So that's where our solution is, as well as over here, 1 is included. Again, going from lowest to highest again, because of the equal to. So 1 with a bracket is included. If it wasn't included, if it didn't have the equal to, we'd use parentheses on it. Comma, we go to the right forever, that takes us to positive. And infinity and negative infinity, again, never have brackets on them with interval notation because they're not specific numbers you're including. It just means it's going on forever. So that's how you write your answer using interval notation. Now let's take a look at one more that's a little bit more complicated because we have a rational expression, a fraction here. Notice this time though it's already got 0 on the right side, so we don't have to worry about that. So let's go ahead and factor the numerator and denominator. The numerator you can see is it's the difference of perfect squares. That would factor in x minus 2, x plus 2. The denominator, we look for factors of -20. Trinomial. Notice neither one of these have a GCF, so there's nothing we could have taken out first. And factors of -20, whose sum is -1. What would work there would be -5 and then positive. And since it's just got a 1 as the leading coefficient, you can jump right to the factored form as x minus 5, x plus 4. All right. Now, both the numerator and denominator, we're looking for where this is less than 0, right? So where it's negative. So both the numerator and denominator, their sign impact whether this is going to be positive or negative. So first we need to figure out what makes a 0 or undefined. So let's look at what makes the numerator 0 and what makes the denominator 0. What makes the numerator 0, we draw our number line in here. Is -2 makes this one 0 and 2 makes this one 0. So -2 and 2. That's what would make 0. And then what makes the denominator 0 are 5 and -4. So let's put those on the number line also. But these come from the denominator. Remember we talked about in section A, if you have 0 divided by a number, that's 0, so these are 0. But if it's something divided by 0, since these make the denominator 0, these wouldn't make the expression 0, they'd make it undefined. I'll just abbreviate it with UND for undefined. But in this case, none of these are going to be solutions. If it had the or equal to, then -2 and 2 would be part of our solutions. But not 5 and -4, because those make it undefined. But it doesn't have the equal to, so none of these are. We just want to see where this is less than 0 or negative. So again, let's test. Here, let's test -5. We test -5, that's the one, -4. Notice we've got 4 different factors to test in here. So -5 makes this factor right here negative. -5 plus 2 is also negative. Negative times a negative is positive. So to make the numerator positive, I'll just write it over here. Divided by -5 minus 5 is negative. -5 minus 4 is negative. Negative times a negative is positive. So the denominator would also be positive. Positive divided by positive is positive. Now let's test something between -4, -2, -3. You don't have to write down the number you're testing. I'm just doing that for your notes, so you can see where we're getting things from. But as you get better at this, you can just keep it in your head what you're testing if you'd like to. So -3 minus 2 is negative. -3 plus 2, also negative. So negative times a negative, still positive on the numerator. -3 plus 5, sorry, -3 minus 5 is negative. -3 plus 4 is positive. So negative times a positive is negative. Positive divided by negative, negative. Now between -2 and 2, the easiest thing to test would be 0. And because 0, -2, and because 0 into this factor, 0 minus 2 is negative, 0 plus 2 is positive. Negative times a positive is negative. So you have a negative on the numerator. And 0 minus 5 is negative, 0 plus 4 is positive, negative times positive is negative. So you have negative divided by negative, that's going to be positive. Then between 2 and 5, that's 3 or 4, I'm going to test 3. So if you test 3 minus 2 is positive, 3 plus 2, positive, positive times positive will be positive. Get positive on the numerator. And 3 minus 5 is negative, 3 plus 4 is positive, negative times positive. Positive divided by negative is negative. So we know everything between 2 and 5 is negative. Makes this expression negative. And finally, if you test 6 over here, 6 minus 2 is positive, 6 plus 2 is positive, positive times a positive is positive, so we get positive on the numerator. 6 minus 5 positive, 6 plus 4 positive, positive times a positive is positive. Then a positive divided by a positive number is positive. So to see where our answers are, we're looking for, look back here, where this expression is less than 0 or negative. So let's again write our answer in inequality and interval notation. So in this case, this interval would be written in inequality notation like this, starting with, and when it's between two numbers, you typically start with the lowest number, -4, is less than x. So it's saying x is greater than -4, but at the same time, x has to be less than -2. In other words, x is between -4 and -2. Or the other possibility is it could be on this interval. Notice I didn't put the equal to because we didn't want it where it was equal to 0, and definitely not where it's undefined, so you just leave off equal to. The other interval is starting with 2. Is less than x. Notice that's saying x is greater than 2 if you flip it around, which is true. But it doesn't just have to be greater than 2, x also has to be less than 5. So this is saying x is between 2 and 5. So that's how you'd write your answer using inequality notation. And then in interval notation, you'd write it parentheses because it's not included, -4, so go from left to right or lowest to highest. -4 to -2, parentheses, and then union, okay, which means including this other interval as well from 2 to 5. And that's how you write your answer in interval notation. Now notice sometimes students think, well, I'm starting to see a pattern. It's positive, negative, positive. Here it's positive, negative, positive, negative, positive. So students think, well, it's always going to be alternating like that. So why do we have to test all the intervals? Let's just test the first interval, and then know it alternates. Well, Even though that pattern holds on these two example problems, and you'll see that pattern a lot, that doesn't always happen. Okay? It doesn't always alternate back and forth. There's sometimes we get two positives next to each other or two negatives next to each other. So because of that, that's why we have to test every interval, because it doesn't always alternate like that, even though it does frequently. It doesn't always happen. And that concludes the notes for AP Calculus on the topics of factoring, simplifying, and solving equations and inequalities using factors.